Hopefully you've had a chance to give this problem a try. I'm going to walk through the solution. And so here we have a list of 4 compounds, and we're being asked which one can be an amphoteric substance. Now, we've spent a lot of time talking about amphoteric substances, but we've only talked about one. We've talked about water being both an acid and a base, but that's our fundamental definition here, is it can be both an acid and a base. So when we're looking at these, we're trying to evaluate to make sure there is both a proton that can be donated and a lone pair that can accept a bond to a proton. So looking through these, let's figure out which ones are most likely to be amphoteric. So right away, like looking at each of these, I see some that are maybes, but I see one that definitely is a no. So this NO2 minus has no hydrogen. So it cannot be an amphoteric substance. Now, my hydrochloric acid and my acetic acid are these two right here. These are both acids. Um, and this is a little bit harder to see that it's unlikely that they'll be amphoteric. I mean, I guess they theoretically could be. It's just not as likely that they will be. So my HCl easily acts as an acid. So we got the acid piece down. That hydrogen can dissociate from the chlorine. This is a binary acid. Uh, but then let's think about it as a base. If it was a base, then HCl would have to gain a proton and form H2Cl plus, which is possible. It's less likely. We don't really see this molecule, but in terms of what we've given you so far, in terms of evaluative power, we don't really, we haven't talked about the structural features that make this less likely yet. So it's harder to see. But in general, it won't actually be a amphoteric substance. And a lot of this comes from the fact that hydrochloric acid is a strong acid. And so a strong acid will rarely form a base. Now, our acetic acid is a weak acid. And we'll talk about what this strong and weak means later. So it can definitely be an acid. Now, if it's a base, we're going to be accepting a hydrogen at the lone pair at one of these oxygens, which is possible. And this happens a lot in, we see this as part of an intermediate in mechanisms in organic chemistry. And so this is a possibility, but it forms a very reactive compound that will react right away. Right. And so we see this as a very transitionary compound. And so it's unlikely. But what it would look like is that CH3COOH with a H plus would form CH3COOH2 plus. And so this I'm just going to put less likely. So the one compound that is a little bit clearer, that is our best substance of these, is HPO4 2 minus. I'm actually going to draw this out to demonstrate what I mean by why it's more likely. So this has an overall -2 charge. And so we have two places. These lone pairs on these oxygens with a formal charge of -1 are great spots to accept a hydrogen. We also have a hydrogen that's attached to an oxygen that's attached to a phosphorus. And so we have an oxyacid structure. And we have negative lone pairs. And so this one far more clearly shows the same pattern for an acid and the patterns that we're looking for a good base. And so our amphoteric substance is going to be this HPO4. So let's write out the chemical formulas for the dissociation for it as both an acid and a base. So I'm going to write out, we'll have let's give ourselves plenty of room. HPO4 -2 plus water will be what we do for both of these. So we're going to call it an acid in one and a base in the other. And so in our acid, when we think of HPO4 2 minus, we're going to donate this hydrogen to our water. When we do that, we're going to form PO4 minus 3 plus H3O plus. Now, if it's a base, that hydrogen is going to come from water, which will be our acid. And is going to be donated to our HPO4. It's going to form a bond at one of these um, lone pairs that have a formal charge of 1 on that oxygen. And so what we're going to do is add a hydrogen to our HPO4 to form H2PO4. And now our charge goes from -2 to -1, and we'll be left with a hydroxide ion. And so here is our acid and base association reactions for this molecule, acting as both an acid and a base in a way that I think is very clear compared to the kind of less likely or maybe scenarios of our acids examples. And in both of those cases, we were forming a positive charge on an electronegative atom. And here we're going from a -2 to a plus, like to a -1, or a -2 to a -3. So it's a little bit more likely rather than adding, because a electronegative atom is going to be like oxygen. It's going to be more likely to support a negative charge than a positive charge.